Hello to everyone from around the world, and welcome to today's webinar, Migrating from 8-bit to 32-bit MCUs, brought to you by NXP and EE Times. We have just a few short announcements before we begin. This webinar is designed to be interactive. Please ask questions at any time during the presentation by typing them in the text area and clicking the Submit button. Our presenter will answer your questions at the end of this webinar, but please enter them whenever they come to mind. Later in the program, we will ask you to complete a short survey. Please take a moment to fill this out and submit it. Your feedback is important to us and will provide NXP and EE Times with valuable information on the subjects covered in this webinar and how we can improve future broadcasts. The survey will open for you at the beginning of the Q&A session. Additionally, you can launch the feedback form by using the survey button. And now, on to the presentation. It's my pleasure to introduce Dave Donnelly, Senior Applications Engineer at NXP. Welcome, Dave. I will now hand it over to you to begin the presentation.
Thank you, everybody, for calling in. Today we're going to talk about migrating from 8-bit microcontrollers to 32-bit microcontrollers. We have a lot of information to cover today, so let's get started. Today we're going to cover a brief introduction to ARM and Cortex-M0 technologies, and then we will cover two migration application examples where we will migrate a CANopen relay driver as well as a battery charger design from an 8-bit microcontroller to 32-bit. At the end there will be a Q&A session. Introduction to Cortex-M0. NXP Semiconductor is a large semiconductor vendor that used to be divested from Philips Semiconductor, and it's been around which was around for about 50 years. They are a large company with about $4 billion of sales per year, and they've been a public company since July of 2010. We have an innovation track record dating 50 years. NXP is a leader in ARM Flash MCU technology with a clear strategy that is 100% focused on ARM. Top performance is made possible through use of leading technology and architecture plus processor cores from designs from ARM. NXP is very committed to the ARM portfolio, and we're the only company to have Cortex-M0, M3, and M4 parts all out at once. Today we will discuss the Cortex-M0, which is the ARM architecture best suited for migration from 8-bit. The slide that you should be seeing right now is the Cortex-M instruction set. This is all of the instructions that are available for all of the parts from the M0 to the M4F. The largest instruction set is in the Cortex-M4, which includes standard microcontroller instruction set plus floating point DSP instructions. Inside of the larger outside box, you will see a blue box, which is the Cortex-M3 instruction set. And then finally, inside of that box, you will find the green instructions, which are the Cortex-M0. So the Cortex-M0 is the lowest area, lowest complexity, lowest cost Cortex processor, which is a good fit for migrating 8-bit designs. NXP has the LPC1100 family, which has the Cortex-M0 core, and this provides the lowest active power consumption of any 32-bit microcontroller core. So the active power is as low as 130 microamps per megahertz. Code density can be 50% less than an equivalent 8-bit part, as we will describe later on in the slides. The LPC1102 is the smallest 32-bit microcontroller available in a 2.2 millimeter footprint. It's designed to successfully address high-volume applications with space constraints. It has also won Best Product for Embedded Systems and ICs in the 2010 EDN China Innovation. This slide shows the Cortex families that NXP has in their portfolio. Starting at the over to the left is the Cortex-M0 1100 family. This is the lowest power family, and the parts run at 50 megahertz and below. All the way over to the right is the Cortex-M4 family, which is the highest performance family. This has integrated microcontroller and also DSP functionality and clock speeds up to 150 megahertz. In the center, there are several Cortex-M3 families, which include high-performance peripherals such as Ethernet and CAN and USB. One of the parts that we would like to highlight today is the LPC11C. This is a total CAN solution. This part has a CAN 2.0B controller on board combined with a CAN transceiver. It also has CAN and CANopen drivers in ROM, and it can support CAN and UART updates with the built-in bootloader. Because of the Cortex-M0 core, it's able to offer higher performance and better code density than traditional 8 and 16-bit architectures. The 1102 that we mentioned previously as the winner of the Innovation Award, this part, although it only has a 2x2 millimeter package, also has 32K of flash, 11 GPIOs, 5 channels of ADC, SPI, UART, and of course the improved performance that the Cortex core can bring it. Active power is down at 130 microamps per megahertz. This brings to a close our first brief section, which is just a background on Cortex technology and the LPC1100 family from NXP. Now let's go into our first application design, which is a CANopen relay driver. Throughout this section, I will be displaying this chart, which will show several ways that this redesign can help save money. So we will discuss how to simultaneously increase performance, save memory, use less power, save money, and make planning for the future easier. As we discuss each section of this chart, I will put a checkbox. There's a checkbox on migration path because we have already discussed the binary code compatibility within the Cortex family. Here's a brief block diagram of our CANopen device. Our device implements an 8-channel relay driver, and it's driven by a PIC18F4585 MCU. So in the hardware is also included a 5-volt voltage regulator and a CAN transceiver. We're going to show how to implement this same design with a 32-bit processor and some of the benefits that will result. The part that we chose for this design, the PIC4585, has 48K of flash memory on board, 3K of RAM, a CAN 2.0B controller, and 10% accuracy internal RC. The way we selected this part was we went to Microchip's portfolio and we selected an 8-bit MCU that was shipping and had a CAN interface on board. This part has a Coremark score of about 1.52 iterations per second at 40 megahertz. When we do the redesign, we're going to replace this part with, we're going to migrate the design to use the LPC11C24. This is a newly released 32-bit LPC microcontroller from NXP based on the ARM Cortex-M0 processor core. This part features 32K of flash, a CAN 2.0 controller and transceiver, a 1% accurate internal RC, 50 megahertz operation, and many other features, and it achieves a Coremark performance of 50.83 iterations per second. There are a few differences between the 8-bit part and the 32-bit part, and I will go through those one by one. The 8-bit part has more flash memory. It actually has 48K to this part's 32K, but this is more than made up for by the code efficiency of the Cortex-M0 core, which we will see later. The NXP part has more RAM, 8K instead of 3K. Also, the NXP part has 2 SPI and 1 I2C peripheral instead of a single combined I2C and SPI peripheral. The NXP part has an integrated CAN controller and also a transceiver, whereas the 8-bit part has just an integrated CAN controller and not a transceiver. There are a few other small differences, but basically these parts are roughly in the same league as far as peripherals go, but the major shift is moving from an 8-bit core to a 32-bit core. Let's get technical and talk about code density and performance for a little bit. It is here that we will see how switching from an 8-bit MCU to a 32-bit MCU can improve our design a lot. This slide shows an overview of the registers that are available on the PIC18F family versus the registers on the Cortex-M0. On the left, you will see in the PIC18 family, there is a single 8-bit working register. There's 2 8-bit product registers for multiply and divide. To access RAM, there's a bank select register as well as file select registers. To access flash, there's a table pointer register. And then finally, there's 9 additional post-increment, post-decrement, and pre-increment registers that are needed to complete the register set. You'll note that many accesses, such as to RAM and flash, need to be done indirectly through bank select or file select registers or table pointer registers. Whereas on the right, if you look at the Cortex-M0 register set, there's 13 registers that are 32 bits each, and those can either store data or addresses. They can be used to access RAM or access flash. And then finally, there's a dedicated stack pointer, program counter, and status register and link register. So the architecture is actually a lot cleaner and simpler for the 32-bit part, which results in faster code execution, smaller code size, and lower power consumption. Let's take a look at a few examples of how the basic core architecture can affect the code efficiency on a microcontroller. Let's compare compiled code. In this case, we're going to look at a few structure accesses through pointers. The code at the top of the slide, the copy info function, copies 2 16-bit values from a from structure into a to structure. The compiled code appears beneath. On the left, the compiled code is generated using the MPLAB C18 compiler, and on the right, the code is generated by the GCC compiler in NXP's LPC Expresso development environment. So looking at the PIC disassembly code, there's a number of addresses that are being accessed, such as FD9 and FE6. These are actually CPU registers that are used to indirectly access the contents of memory. Many instructions are required to do the pointer arithmetic in order to access the data records in the structures. Because the data that we're accessing is 16-bit values and it must be accessed 8 bits at a time on an 8-bit architecture, even more instructions are required. On the right, in the Cortex-M0 instruction assembly code, the load and store operations use the function arguments registers R0 and R1 to indirectly access data, and then R3 is used as temporary storage when moving the data. So looking at this code comparison, it seems that the PIC18F architecture struggles to handle standard C pointer operations, which can lead to inefficient code. Let's look at a 32-bit multiply example. In this case, the code is similarly compiled with optimization enabled. You'll notice that 20 instructions are needed on the left to fetch the multiplicands, which are the values to be multiplied. Then a function is called to do the multiply operation, and 8 instructions are used to store the product. On the right, in the Cortex-M0 assembly code, 2 instructions are needed to fetch the data to multiply. A single instruction does the multiply, and then finally 1 instruction saves the results. One thing to keep in mind is that the pick instructions on the left take either 4 or 8 CPU clocks because of the divide by 4 architecture. The Cortex instructions take 1 or 2 CPU clocks, so they execute much more quickly at the same clock frequency. In general, 8-bit architectures do not handle math operations as efficiently as 32-bit architectures. In this case, the data move operations also waste time and code space. This is our last compiled code comparison example, and this is for I/O bit sets and clears. I/O bit sets and clears are used to manipulate I/O pins. An engineer might have to implement many bit sets and clears to communicate with an existing submodule or IC. Traditionally, this has been difficult to do on older 32-bit processors. On the LPC1100 family, the GPIO ports have word addressable registers to access each combination of bits on the port. This means a simple store operation can set 1 or more bits or clear 1 or more bits. Because of this NXP enhancement, code generated to set or clear a line of I/O is very similar between the 8 and 32-bit processors, except for the use of a store instruction to replace a read, modify, write instruction. Since the 32-bit Cortex-M0 architecture takes fewer clock cycles per instruction, it's able to more efficiently set and clear the I/O lines in the 8-bit device, even though it takes the same number of instructions. So this allows implementing faster communications through GPIO. So if you have any kind of bit toggling requirement, this provides better performance. So I've mentioned Coremark spec a few times. So let me just talk about what that is, and then I will describe the results. Coremark is a synthetic benchmark of CPU core compute efficiency. Results are usually given as iterations per second, which is called Coremark, or iterations per second per megahertz, which is known as Coremark per megahertz. This is ANSI source code that's freely available, and it includes a number of standard operations such as linked lists, matrix operations, CRC calculations, as well as state machine control code. Standard C types are used. Those can be 32-bit integers, 16-bit integers, pointers, and etc. And about 2K of RAM is required. The Coremark code and scores are available from coremark.org, which is brought to you by EEMBC, the Benchmark Consortium. This is the Coremark performance results here in this slide are based on using a microchip C18 compiler without the procedural abstraction optimization, because the PA optimization reduces performance. On the LPC1100, we use LPC Expresso GCC, which is the free compiler with the -OS size optimization. In this case, the PIC was running at 40 megahertz, and the LPC1100 was running at 48 megahertz. It's worth pointing out that because the performance is so much better on the 32-bit platform, it can often be operated at lower clock speeds than the 8-bit MCU it is replacing, which can save power. Looking at the code size for the benchmark, this is actually how much code the same benchmark takes to compile for PIC18F family versus LPC1100. In this case, we turned on the procedural abstraction optimization because it reduces code size. And still, this shows that you need over 3 times the amount of flash memory to run the same code if you use standard C operations such as pointer operations and 32-bit math. That takes care of showing the code density and performance advantages of migrating from 8 to 32 bits. Let's discuss some of the power advantages. Although the LPC1100 family of 32-bit Cortex-M0 MCUs achieves much higher performance and operates at a faster clock speed, current consumption is lower. When operating at 40 MHz, the typical current consumption for the PIC18F4585 is 23 milliamps. Typical current consumption for the LPC1100 family is 7 milliamps when operating at 48 MHz. This is about 70% less current consumption. There are many reasons for this. Partially, this is the result of improved dynamic characteristics at the smaller process node used by the LPC11C24. Partially as a result of newer power management techniques in the 11C24 that allow more efficient operation, such as the ability to clock gate peripherals when they are not being used. Power down current, which we call deep power down current because we have more power down modes, is also lower. The LPC11C24 also offers a deep sleep mode, which has no equivalent in the 18F4585. As you can see, run power at maximum speed is much less. Given the increase in performance, the speed could be reduced further, and the amount of time spent in run mode could also be reduced. Back to our migration. Let's take a few minutes to go through the steps that need to be completed to migrate the design from 8-bit to 32-bit. The first step is to migrate the MCU to a 3.3-volt power supply. In this case, the original design used a single 5-volt power supply to power the microcontroller, supplied by a 5-volt linear regulator, which also powers the CAN transceiver. The LPC1000 series of MCUs can run from 1.8 to 3.6 volts. Although the GPIOs are 5-volt tolerant, the LPC1000 family cannot be powered directly from 5 volts. We handled this in our new design by adding a 3.3-volt power supply and connecting it to the MCU. In this case, we decided to use an LDO and a SOT23 package because our design will only draw an absolute maximum of possibly 20 milliamps from the 3.3-volt supply, or only about 66 milliwatts. No special provisions for heat sinking are needed on the PCB. Our next migration step is to migrate the microcontroller functions to new pins on the LPC11C24. In the PIC design, we have the Darlington drivers connected to port D. In the LPC version of the design, we moved the Darlington driver array to port 2. Also, since the 11C22 has a built-in CAN transceiver, that part is removed from the schematic and the CAN signals are connected directly to the onboard transceiver. In a more complex design, pins would have to be selected based on their individual functions, such as whether they supported analog input or I²C. Our next step is to relay out the PCB. Swapping MCUs from an 8-bit part to a 32-bit part is likely to change the pinout. The MCU portion, at least, of your PCB will have to be redone. I would like to take this moment to point out that a small amount of board space is saved. This comes partially from not having to include the CAN transceiver and partially from the smaller package footprint of the LPC part. Now, all that is left to deal with is the software. One of the most important migration tasks is handling the software migration. First, a development tool suite must be chosen. Many developers new to the Cortex-M0 will end up starting their development using LPC Expresso because LPC Expresso is NXP's low-cost, fully integrated development tool platform for the LPC MCU family. LPC Expresso consists of an Eclipse-based IDE as well as a target board that includes a debugger. The IDE is free and the boards are $29. The IDE includes a free GCC compiler with optimization that doesn't expire. It includes project templates for NXP ARM-based MCUs, Synthesis libraries, C libraries. It also includes a source-level debugger. And the LPC Expresso ecosystem includes a number of add-on boards by embedded artists. The LPC Link debugger, which is part of LPC Expresso, can debug either the target that is built into the board or external targets. LPC Expresso is supported under Windows as well as Linux. It supports all of the Cortex-based processors from NXP and a number of ARM7 and ARM9 devices. The LPC Link debugger that is part of LPC Expresso implements both JTAG and SWD ARM debugging with a built-in ARM9 controller. And it makes it possible to experience the same user interface from initial conception of your project all the way to final code development and testing. If there is a 128K code space limit in LPC Expresso, however, there is a migration path to the Red Suite from Code Red to support larger code sizes. Any discussion of LPC development tools would not be complete without discussing third-party tools. There are a number of fully featured development tools such as the Kyle and IAR, High-Tex, and other suites. There is an online development tool called Embed, which is also available, in addition to LPC Expresso. Because NXP has focused on ARM and Cortex cores, these professional-grade tools are available to seamlessly support NXP's line of microcontrollers. And it's so the customer can choose whichever tool is the best fit for them. I would like to take this opportunity to point out that the LPC Expresso IDE and debugger, as well as the professional third-party tools, support all of NXP's ARM and Cortex LPC families. This makes migration easy. You can start with the 11C24 and move to the 1768 or 69 later, which support Ethernet in addition to CAN. So we're still on our fourth step of our migration, which is migrating to the new toolchain and using the NXP libraries. So some of the NXP makes available a set of peripheral libraries plus examples, which cover all of the peripherals on the chip. For example, the ADC, GPIO, there's also a CAN example. There's a CAN example that uses the on-chip driver. There's a Power API demo. These are all can help porting code, make porting the code much easier. These examples are free of charge, and they come in several forms. They come in the form of an examples bundle that targets each peripheral on the part, and they also come in the on-chip ROM. NXP ROM libraries are free, and they work with all of the tool chains available for the LPC1000 family of MCUs. There are 3 ROM libraries that are available on LPC1000 family today. One of those is Power Profiles, which allows you to tune the dynamic current of the part. You can run the part either in CPU performance mode, where you get the highest CPU performance, or you can run it in lowest active power mode or CPU efficiency mode. Because the Cortex-M0 family core does not have a hardware divider, there is a ROM divider library, which is very efficient, and it also gives you the same results across all of the tool chains. Finally, there's a CAN and CANopen driver that is included in ROM on CAN-capable parts. NXP has USB drivers and other LPC parts and has plans to provide even more functionality in on-chip ROM. For our small relay driver project, the most important library is the CANopen driver. The CANopen driver provides an easy-to-use API for the CANopen protocol. It also supports a CAN bootloader, which allows flash updates over the CAN interface. The driver saves flash memory by being incorporated in on-chip ROM. So let's get to the last benefit of our 8 to 32-bit migration. We've achieved a BOM cost reduction estimated at about $3 in 1K quantities. So that's $3 per unit. This comes from the green on the BOM shows components that are unchanged, and the yellow marks things that have changed. As you can see, despite having to add another power supply for the 11C24, there's a big overall cost savings. This comes from the MCU price cost reduction, and then also the integration of the CAN transceiver IC. The BOM on the last slide shows the pricing advantage of 32-bit versus 8-bit. Let's look at a different migration example from an NXP LPC11C00 part. Our goal is to show how to migrate an existing 8-bit ADC51 design. This is based on NXP application note 10338, and the code is available to everybody on the NXP website. Our battery charger is implemented as a simple buck converter. The battery charger design takes an input voltage of 5.1 volts, and it charges a single 700 milliamp hour cell, lithium-ion cell. Why would someone migrate such a simple design from 8-bit to 32-bit? So as it happens, there is a cost savings. The 32-bit MCU that we suggest for this is the LPC1111, which is priced slightly less than the LPC916. Another cost saving is that the higher speed of the 1111 allows using a smaller inductor value in the PWM. The main reason to consider this migration is the enhanced functionality. There are 28 I/O pins on the 1111 versus 14 I/O pins on the 916. The processor performance is much faster on the 1111. And then there's more flash memory available, 8K flash versus 2K flash. So with all of these extra resources, it's possible to add more features and increase the scope of the original design. What used to be a single-cell battery charger could turn into a single-cell battery charger that also has speakers and a remote control without having to add to the microcontroller cost in the unit. This is a block diagram of the LPC916 8-bit microcontroller. It has 2K of flash and 256 bytes of RAM. The migration tasks for this design, we're going to go through this all very quickly in one slide, but basically it's necessary to change the microcontroller and inductor and relay out the board. For the toolchain and the code migration, the original design was done using the Kyle third-party tools on the 8051, so we were able to migrate to the Kyle Cortex development tools for the LPC1100 family. So we're actually able to keep the same tool suite and migrate from the 8-bit part to the 32-bit part. And then finally, the code can be migrated using the libraries that are available on the NXP website. For instance, there is an example of using the PWM, and there's a PWM library. There's also similarly for the ADC and GPIO. For the schematic and PC board, we ended up recreating it using different EDA tools. If the same EDA design and package are available, then it's possible to get away without having to recreate the entire layout from scratch. This slide shows our reuse of the code from the NXP sample software library. To migrate the code for the battery charger app note, we needed to add to it a new startup code for the ARM. There's a system_LPC1100XX.C, which is used for clock configuration, core_CM0.C, which is a census library, and then we add the ADC and timer modules to our code library, and this makes it very easy for us to port the code from the 8-bit part to the 32-bit part. Now let's talk about some resources that you can use to help get started on migrating a design from 8 bits to 32 bits. There are many links to get started. I apologize to everybody. As I understand in this live presentation, these links are not clickable, but the presentation will be recorded and then the links can be accessed later. There is an MCU homepage at NXP's website. In the LPC zone, there's many product updates and training. The NXP LPC Expresso site has a lot of information on our low-cost development tool. And then finally, mbed.org is a good place to go if you're interested in rapid prototyping without having to install any software at all. There is an offline NXP microcontroller selection guide. This can be used to help pick the perfect part. One of the things that we've been working on recently is training videos. Sometimes a video is worth more than 1,000 words. We have introduction to the different processor families, walkthroughs on using the debug tools. We have some walkthroughs that discuss different peripherals that are available on our parts, and as well as how to use the LPC Expresso tool. Some of our latest webinars include fundamentals of microcontrollers, how to market, first to market Cortex-M0 microcontrollers, and also introduction to 1700. And then here are a few books that have been released recently on NXP products. Finally, to help get the word out about Cortex-M0, its very low cost and high performance 32-bit capabilities, we have a Simple Choice Worldwide campaign. If you visit this link, you can see many design examples as well as videos for people that are showing how they've shifted from an 8-bit microcontroller to a 32-bit part. To keep tabs on release of new documentation as well as new products, check out our social media on Twitter, YouTube, and Yahoo. That concludes the presentation portion for today. I hope you will all stay for the question and answer section.
Thank you, Dave, for a great presentation. Before we start the Q&A, I would just like everyone to note the survey on your screen. And if you don't see the survey, please launch it now by clicking the survey button on the left side of your interface. Thank you in advance for filling it out. Your responses are very important to us, and we'll provide NXP and EE Times with feedback on how we can improve future webinars. We'll now move into the question and answer section of the presentation. So if you have a question for our presenter, please submit it now by typing it in the text area on the left-hand side of your screen and click Submit. And with that, I'll hand it back over to Dave to kick off the Q&A.
Thank you very much.
Okay, so it looks like we have a lot of questions that have come in. So go ahead and open the Q&A tab and let's get started.
All right, just one second. Just bringing up the questions right here. Sorry about the delay.
Would you like me to read some of them?
All right, so I have a question here. Are there any plans to release a Cortex-M0 microcontroller with USB on board? The answer is yes. We're rolling out a USB series in the very near future. Please contact your NXP local sales office for the latest information. Let me see what is next on here. I have a question from, I'm unfortunately not sure how to pronounce this person's name, but the question is, in your benchmark, you mentioned turning on and off an optimization that affected both code speed and code size. Can you restate how that optimization changed the results and whether it was the same in both comparisons? So I believe this question is related to the results that I have under the, when I was comparing the Coremark benchmark results with the PIC part versus the LPC1000 Cortex-M0 part. So it turns out in the compiler that we were using, the MPLAB C18 compiler, there's an option called procedural abstraction. And when that is turned on, the code is smaller, but it doesn't run as fast. So we actually ended up doing the code size benchmark with this optimization on so that we could get the best code size results for comparison. And then we did the same benchmark with the procedural abstraction turned off to get the best performance comparison. So we actually tried to do it the best that we could on both parts and then compare them at their best. So we didn't use the optimization to disadvantage the competitor or even just leave it at the same option, which would allow it, to look better for code size and not as good for speed. So I hope that answers that question. Next question here is, is there any LPC Expresso with the CAN version of LPC1000 planned? The answer is yes. Those will be available next month at distribution, and the part that will be on the board will be the LPC11C24, which is the same one we talked about. Next question is, I'm assuming this training video is also recorded and will be available for playback. Will you provide the link to the attendees after the conference call? Yes, you will receive a notification once the event is available on demand. It usually comes in about 24 to 48 hours. What of the new LPC products / LPC Expresso will be shown at the Embedded World in Nuremberg? We will showcase several demos, including a demo for our new LPC1200 Cortex-M0 series and the LPC4000 Cortex-M4 family. How can we get a PowerPoint presentation copy of this presentation? You can find a downloadable PDF of the presentation under the Additional Resources button in the console. This PDF will be regenerated and uploaded later today because apparently there's some images missing from it. Here's a good question about CRP, which is code read protection. Is there a document discussing the effectiveness of the CRP with respect to the types of attacks that can be prevented and what attacks cannot be evaded? That's from Carl. Yes, there is an app note that describes the CRP usage. It is AN10851, and it's got a lot of good detail on it. There's also an app note that was for the 1700. There's one for the 1100, which is application note 10968. Here's a question. Is there a plan in the LPC1100 roadmap to include Ethernet controller along with CAN? So unfortunately, we have no plans at this time to roll out an LPC1100 with Ethernet and CAN, but we do have the LPC1768 and 1769 series today, which it's a Cortex-M3 core part that has Ethernet as well as CAN. Here's a question. Is there a command line GCC compiler for these parts? The answer is yes. Actually, if you don't want to compile it from scratch yourself, you can use the LPC Expresso toolchain, which is based off of GCC and Eclipse as the IDE. So if you install LPC Expresso, it will install a command line GCC compiler. And it's available for Linux as well as Windows. So if you don't want to use Eclipse under Linux, you can install LPC Expresso just to get a complete finished GCC toolchain and all of the libraries and include files and everything installed easily. Here's a question. Why is there a code size limit on LPC Expresso? Please note that the code size limit is actually 128K, which means that for the LPC 1100 family, there's no limit because the largest part in that family is 128K. There is actually an upgrade available to 256K for $256 and 512K for $512. So the upgrade costs are pretty reasonable, and they're mainly to pay the cost of support. Here's another question. The question is on the LPC 1200 series. Why does this series run only at 33 megahertz? This series is specifically customized for industrial control applications, and it runs only at 33 megahertz because of this. On the other hand, it gets very good power performance as well. Anybody, if anyone else has any questions, please put those in. Here's a good question. Which Cortex-M0 microcontrollers have a hardware multiplier? The answer to that is all of the Cortex-M0s from NXP have a single cycle hardware multiplier on board. It's a 32 by 32 multiplier. Do you plan to launch new chips with USB host on board? The answer is we already have solutions with on-chip USB host controller support. Please visit our website for more information. Again, one thing that might help is to probably check those out in the Cortex-M3 family as well as the ARM7, ARM9 family. Those are not present in the LPC1100 family. How would you advise the connectivities with Zigbee and wireless peripherals? The NXP Cortex-M0 parts support SPI and UART interfaces to connect to these types of devices. Here's a question. What about non-volatile memory? Why did NXP not make any mechanism to emulate EEPROM in Flash? We have an application note on emulating EEPROM in Flash, which I'll give you the app note number soon. But we also are rolling out LPC1100 family parts soon that will include support for hardware EEPROM. The application note for emulating EEPROM is AN11008, published January 5th, 2011. Here's a question. It says, you can work with variables of type bit with Cortex-M0. The answer is yes. So that is done in the compiler. There's no special work that needs to be done. Bit field variables can be declared and used.
Dave, it looks like we have time for about one more question.
All right, let me find a good question here. Is there a Cortex-M3 based version of the low-cost LPC Expresso board and toolchain? Sorry about this. I didn't have time to actually, I should have maybe gone through all the boards in the presentation. There's an LPC Expresso 1343 board, which is a Cortex-M3. There's a 1769 board that is also Cortex-M3. There's also the 1114 11C24 board that's just coming out, and those are Cortex-M0 boards. And that looks like that wraps up the questions for now.
Well, thank you so much, Dave. And I would like to thank everyone for attending today's webinar, Migrating from 8-bit to 32-bit MCUs, brought to you by NXP and EE Times. Please fill out and submit the survey at this time if you haven't done so already. By completing this survey, you will provide NXP and EE Times with valuable feedback on the subjects covered in this webinar and how we can improve future broadcasts. This presentation will be available shortly in an on-demand format, and as a registered user, you will receive an email with detailed information on how you can access the on-demand replay of this webinar. The on-demand will also include a PDF copy of the slides used in today's discussion. This webinar is copyright 2011 by EE Times. The presentation materials are owned by or copyright by NXP, which is solely responsible for their content. The individual speaker is solely responsible for his content and opinions. We hope you will join us for future webinars. For a current schedule of live and on-demand events, please visit us at eetimes.com. Thanks for joining us and have a great day.